So tonight's speaker is Dr. Isaac Smith from York University, talking about a high-resolution view of icy Mars. Just a brief background on Dr. Smith. He got his master's in physics at the University of Missouri St. Louis in 2007. Got his PhD in geosciences at the University of Texas at Austin. And did his postdoc work at Southwest Research Institute in Boulder, Colorado. And since 2018, he's been the assistant professor and Canada Research Chair at York University here in Toronto. Ladies and gentlemen, Isaac Smith.
Thank you very much for having me. It's a pleasure to be here at the Royal Astronomical Society of Canada, and I hope you enjoy what I'm about to say. So I'd like to talk to you about icy Mars, but a high-resolution view of icy Mars. Here I've got one of my favorite images of all time. It was taken a couple years ago by the high-resolution stereo camera. And each slide, I'm going to have the name of the camera that took the picture. What I really enjoy about this is you can see the North Pole, which is one of my favorite topics to study on Mars. There's these giant spirals, some of them 800 kilometers long, spaced 70 kilometers apart. There's this canyon here that's the size of the Grand Canyon, and you can actually see wind pushing dust out of there. It's a very active environment. Around the edges here, you can also see wind blowing clouds away from the pole. And this is pretty interesting because we can capture these things in great detail with our new cameras. There's also these darker sand dunes that surround the polar cap, which are very active. Some of the most active places on Mars, we see these things move up to meters per year. Similar transport rates as we see with sand dunes on Earth. And then as you go farther away, you can see great geologic features, outflow channels, there's craters, and then there's the limb where we have more clouds and dust hazes that we can see too. And so this is just a really exquisite photo, and I'd like to show it to everybody. Before we get into too much detail with the high-resolution cameras, I'd like to point out a few of the major details on Mars. We're going to use global topography. This was taken with the Mars Orbiter Laser Altimeter, we call MOLA. It's really important because prior to about 1998, we had very little topographic information. It was really just looking at shadows that we could get this. But as you can see now, we have these great, very large features, including these volcanoes. The maximum elevation on the planet is Olympus Mons. Many of us know that. It's almost 30 kilometers higher than the minimum elevation at the depth of Hellas Basin. So there's a huge variety of Mars in topography, much greater than the Earth. There's a series of enormous volcanoes that cover this area we call the Tharsis Rise. It's a giant volcanic province centered near the equator. The equator is approximately here. And then we have a global dichotomy where we have in the north this basin that is one of the earliest features on Mars. And in the south, we have what we call the highlands. And so there's quite a few kilometers of topography separation between these two. Because of all the craters here, we know that the south is much older and the north is quite a bit younger. And that's not because it's the oldest feature, but it's because it's infilled over time, probably with ice and a lot of settlement due to some of these outflow channels. There's other great basins. So this is Isidis, this is Argyre, and there's another one called Utopia, approximately there. These large circular features that were formed early on in Mars history through giant impacts. I mentioned the outflow channels. Valles Marineris is this giant canyon here, which is wider than the continental United States or Canada. It's many thousands of kilometers wide, hundreds of kilometers across, 8 kilometers deep. So this is a very enormous canyon, formed mostly by tectonic separation of the plate. During that time, there was a lot of outflow, so water was, along with the volcanic materials, water was coming out of the surface, and it flowed out and cut these channels probably relatively quickly in Martian history. And, of course, that might have flowed into the northern basin and filled that in to make it smooth. This is the earliest photograph I could find of Mars. It's not a true photograph. The very early cameras were television cameras. They didn't have a way to store film. You couldn't send film to Mars and then send the image back. And you didn't have CCDs. So what you had to do is live television, and you'd scan, and you could see how Mars rotated a little bit in this. But it's just really amazing the technology that they used back in the late 60s with this Mariner 7 on one of the first flybys. Since then, we've had the Viking Mars orbiter, and it was able to use the digital image model, or Okay, this is MDIM, which is a color imager. And we've had it here projected onto cylindrical projection. It's not the best projection, but it kind of gives you an idea of the difference in colors that we can see. We can see dark material, lighter, dusty material, and then all the ice. And there's a bunch of clouds too. We couldn't see this with the original detail from the previous camera. This is a better version of the same camera projected onto the sphere, and the colors are slightly off to enhance it and make it look real great. And of course we can see the much higher detail now with the canyon, the volcanoes are there, the outflow channels, and of course there's a lot of impacts too. I'd be remiss, I'm a radar scientist primarily, and I'd be remiss if I didn't show radar images. The resolution here is about 3 kilometers, so that's not nearly as great as we're going to see later. We have cameras that could see you as a person or your shadow down to about 25 centimeters, which is quite a bit better. But the radar is really important because with a single Arecibo observation, we could see many of the recent volcanic lava flows on Mars. And when I say recent, some of them are as young as 10 million years. And when you think about geologic history, that's actually just a really short time frame. And so some of these are just a few million years, or 10 million years or so. And of course, there's the giant volcanoes here, which are hard to see in the volcanic map because we're not used to this. Radar detects reflection from scattering. And so it's not a true image. It's one that we build and we process to get this. Hubble Space Telescope is another observation, another technique we use, another instrument. It's, of course, not at Mars, but like Arecibo, we can see Mars with this. And here's a 2016 image showing these beautiful clouds. There's the southern ice cap. There's actually, you can see the northern cap fully, and the southern is partially covered by CO2 ice. We're going to talk a lot more about CO2 ice in a little bit, and there's a lot of clouds here. Just a couple years later, from a similar vantage, so we see this low or high albedo crater with it's not very dark. It's the same one as there, so it's nearly the same orientation, but many of the details are gone, and that's because in 2018, last summer, we had a dust storm that covered our view of the planet. In fact, some places it got so we couldn't see the surface at all with any instruments. And so quite a big difference between these two. And I'm going to talk about dust. This is a Marcy image. So Marcy is the Mars Color Imager. It orbits Mars every 2 hours on Mars Reconnaissance Orbiter, and it takes these swaths. And these swaths, over time, will build up a whole image of the planet. It's every 2 hours. However, it's an inclination so that it always crosses the equator at 3 p.m. And so this is 3 p.m., that's 3 p.m., this is 3 p.m. So you're always looking at the same time of day as you go around. You're not going around the planet's turning under you. And so there's a lot of dust in here. You can't really see it, so I'm going to show the video that'll give you an idea of how the dust propagates. And you can see the dust storm growing right there, and it goes around the planet. So we call it a planet encircling dust event, PEDE. Global dust storm is not the favorite term anymore because it doesn't completely cover the globe. As you'll notice in the south, there's very little dust cover. That's because it was southern spring and the winds were very strong there, and so the winds pushed the dust away and actually left the south mostly uncovered. The north is in polar night, and so we don't have any images from there. But our other observations told us it didn't get very dusty there either. There's a polar vortex which protects the North Pole from having the dust move in. And then here's another image. It's kind of the same where we can actually track the dust with color. And so you can see how far it travels around the planet, eventually encircling it. And unfortunately here we have the 2 rovers. This is Odyssey. Odyssey was right under where the event started. And it got so dark there that it was like wearing solar eclipse glasses. There was not enough light to charge the solar panels, and of course we lost the rover. Curiosity rover is in Gale Crater. It didn't get nearly as much dust, although it observed it quite well, but it also doesn't run on solar power, so it was able to survive. This is a similar map using the Marcy camera, and we can see how the Mars is rotating under the camera, and you can get these dust storms. This is a longish video, so I'm not going to show all of it. Over time, the dust picks up, but we got a good idea from the previous images. And this is a little bit later with the dust covering a lot of the planet. There are diurnal cycles, so the dust gets elevated during the daytime when we have convection pushing it up, and at night it cools down and it settles. And so that's why there's a difference between east and west within a single strip. you can see that on the west it's going to be a little bit warmer and more convective. Okay, I'm going to use the Mars orbital camera now, which is a little bit better resolution. This is the wide angle, but it still gives us much more detail than Marcy. And here's what a dust storm might look like near Valles Marineris. Here's another one near Noctis Labyrinthus, just on the other side of Valles Marineris. There's quite a bit of dust being pulled up, often by wind. Wind, we think, is the primary driver for causing these dust storms. Here's one of my favorite images of Mars. Besides Hubble, it's really hard to take an image of the full disk. That's because a lot of our cameras are very high resolution. As I mentioned, we can get down to a few tens of centimeters. And they're really looking at these, what we call postage stamps. You have to step far back to get the full disk image. And there's only one camera that can do this at Mars right now, and it's the Indian Space Agency's Mars Color Camera, MCC. And it has a very elliptical orbit. And in that orbit, it gets far enough away that you can get the full disk. I really enjoy this one. As I mentioned before, the North Polar Cap is one of my favorite places. You can see that quite well here. You can see the sand dunes, all the different materials. So if you're not familiar, the lighter materials tend to be rusty. It's iron oxide. That's why it looks red to us when we look in the sky and also on the surface here. But there are different gradations of that. The lightest places, besides the ice, the lightest places are dusty. So they might have centimeters to meters of dust. That's this high albedo light color. The places that are darker are generally volcanic terrain, more recent. Hesperian age was the second age of Mars, on the order of about 3 billion years. And so these are volcanic terrains that are quite a bit younger than the oldest Noachian terrains that are heavily cratered. And so it hasn't had as much time to rust yet. The other dark material is basaltic sand, probably eroded from those volcanic terrains. And often when you see a crater that has dark material in it, it's because it has the sand that was eroded from the basaltic lava flows. And so it's a mix of sand and competent rock. Here's another one from ISRO. This one I like because it has the polar hood. The polar hood is really interesting. Every winter in either hemisphere, we get these clouds that cover up the surface, and it also stops some of the radiation from the surface, keeping it a little bit warmer than it might be otherwise. Of course, we have these the major volcanoes and Valles Marineris again as landmarks. And there's this little bit of dust right here coming off of the pole. There's a polar vortex, and just like on Earth, it pushes the dust away from the planet, or from the polar caps. Here's another one from the MCC. The North Polar Cap is still icy. This is the seasonal ice, which is a CO2 frost. The image I showed you before, there's no CO2 anymore, so it's completely uncovered, and the water ice is exposed. And this one doesn't have any exposed water ice. There's these great clouds set up by the circulation, the atmospheric circulation of the planet, where we have winds from the east that blow over the volcanoes, and then as the gas expands, it cools, and it gives us these clouds just downstream of the volcanoes. There's another one there, for example. Here's one that looks like the volcano is smoking. You may remember the press release a little bit ago. Mars does not have an active volcano, although it may look like it. It's just another example of these types of clouds and a very narrow wind stream that causes this. The other volcanoes aren't doing it. So it's pretty cool to see this, and Mars can always throw surprises at us, which we really enjoy. Oh, and then I should say this is taken by the high-resolution stereo camera on the European mission Mars Express. So I call that HRSC. That was also the first image I showed. Here's some more ISRO images, zoomed in quite a bit. As I mentioned, it has an elliptical orbit, so sometimes it's very close and you can get higher resolution, while sometimes it's far away, you can get the full disk. Here's Olympus Mons. You can see the clouds downstream, and here you can see some more clouds there. And so better view, we can see actually more detail in the clouds, how they're thicker and thinner in different places. Okay, so I mentioned the polar hood and the seasonal cap already. And in this one we have dust trailing out because the polar vortex is broken. We see this in other places too. So this is an example of where dust is being pushed away by the winds coming off the polar hood. And this is a better image of the seasonal cap. Okay, and this is the ANISA Rosetta Osiris, which is, it was a camera that was designed not for science, but it was actually an operational camera they were using. And so let me rephrase that actually. I got that backwards. This is the Rosetta mission that flew to Comet 69P that they went and landed on a few years ago, and they had a close flyby of Mars, and so they took this image while they were flying by Mars. Please excuse that. Okay, and then this is a really great image of dust coming off the polar cap right here. This is using Mars Orbital Camera. It was a camera that arrived in the 90s, and it could take these larger views. Here's the North Polar Cap. The water ice is covered by CO2, and then there's a ton of dust coming out. It turns out that there's very repeatable patterns of dust storms that come off the North Pole several times a year, and so this is just one of them that we can predict, actually. Yep. And this is using the visual monitoring camera on Mars Express. This was the operations camera, not the science camera, but they were able to track a dust storm in action. So this is a dust storm. You can see it moving. And it moves pretty fast, actually. So that's really cool that we can see that. So this was the operation camera. Okay, and then back to HRSC. Here's the front. And so the winds just like on Earth, have big fronts. And so we can see the dust moving from the right to the left. And in this case, it's moving over a beautiful dune field, which is not a saturated dune field. It doesn't have sand everywhere. So we have these dark olivine and pyroxene basaltic sands flowing across the lighter tone material. It makes this really stunning image when the contrast between that and the atmosphere are outstanding. And this is using the same camera. And so here you can actually see two motions. So there's one going this way, and there's one going a little bit different. A stereo camera takes two pictures, so it looks forward, and it passes a little bit, and it turns around and looks back. And so we can get some motion because we can reproject these together. So one of the motions you see is actually parallax caused by this change in the camera angle. And that's the higher ones. But the other ones are true motion by the clouds across the ground. And so this is a really cool camera because we can see clouds moving on the order. This is on the order of seconds that we see this much detail. Okay, I mentioned before about Mars Orbiter Laser Altimeter. It's a great instrument. They gave us this. We understand now the global dichotomy. We understand the volcanoes and everything. We also understand that the polar caps come a few thousand meters above the surface. So the North Polar Cap's about 3,000 meters above the basin it sits in. The South Polar Cap is the same. It's much harder to tell on this one because the elevation is much higher surrounding this, so it's not really a basin it fills. It sits on top of these rockier plains. There is the Promethea Planum, which is a basin there, but only is under part of the South Polar Cap. The South Polar Cap is higher than the North by about 6.5 kilometers and has a strong effect on the temperatures there and the seasons. But the biggest effect is actually caused by the South Polar Cap, which comes down to almost 70 degrees south, where the North is almost entirely bounded by 80 degrees north, and it doesn't reach down here. And so the ice that's here gets much warmer much earlier, and the sun affects what's going on right here a lot more. So the seasons on the South Pole are longer because it's much more extended in latitude. Okay, so this is the young terrain, and this is the older terrain. Here I've bounded it so that you can see a rough estimation of where the South Polar Cap resides, because it's not so obvious when you look at it without the bounding. But actually, this is a better way to see it. Here's the limb. We're using HRSC again. So we can see most of the southern hemisphere, at least in this swath. The South Polar Cap is here. And then this is CO2 ice. So unlike the North, where we have water ice covering the surface, here we don't have that. We have CO2 ice that sits there. What we're looking at is on the order of a few meters to 10 meters thick, and it's extremely bright. We can see this from Earth, even with low-resolution telescopes. And so it was really impressive. We knew it was CO2, and so there were some indications or some beliefs that early on we thought that the entire South Polar Cap could be CO2. We know that's not true now. It's really just a thin deposit sitting on top, where the rest of what you see in here is water ice. And unfortunately, you can't see it because it's not white, and that's because it's covered by a thick lag of dust. A dust lag can accumulate different ways. One, it can fall from the atmosphere, but a more likely way is that when the ice snowed out, there was dust as the depot centers, and it brought dust with it. Some of the ice sublimes, leaving this dusty material on top. And so we don't think it's very thick, maybe a couple centimeters, but the effect is that it covers up the water ice perfectly, and you can't see it very well. As I mentioned in the North, there are spiral troughs. There are spirals here. They're not as well organized, but they're still pretty stunning to look at. So red is water ice covered by dust. White is CO2 ice. Here's a perspective view with some topography. You can actually see how the CO2 kind of sits in these basins, which are the spiral troughs. And some of them, they just sit in closed basins where you have a nearly level top. So this is Viking image over topography. Using the context imager, which is CTX, we call it on Mars orbital MRO, Mars Reconnaissance Orbiter, we can build up these mosaics. CTX does these pretty large strips. If you build up enough over time, you can get this whole area. And so with this, you can see a ton more detail. Besides the spiral troughs, you can see fine detail in the surface of the CO2. And there's sublimation pits and there's other things I'm going to zoom in on. So we're going to look here next. This is using the context imager, but at full resolution. You can see there's a big change approximately here between this water ice section and then the CO2 ice section. In the CO2 ice, we have what we call Swiss cheese terrain. It's pretty obvious why. The sublimation pits move outward. This is how we know that the CO2 is only a few meters thick, and that's because the top to bottom of that is only a few meters. And it repeats up here. We have a different type of Swiss cheese terrain with smaller pits and then some more lineations there. But this is all caused by CO2 on the surface. And then using the high-resolution imaging science experiment, also known as HiRISE, we can zoom in much farther down to the meter and submeter scale. And here what we have, the classic thumbprint terrain. It doesn't cover the huge area on the South Polar Cap, but we can monitor this from year to year, and we see it moves just a little bit. And so the thumbprint terrain is a really cool part of that cap. Here are some sublimation pits where we can observe that something below is subliming, and then they get filled in with more ice. This is again from the context imager. And these pits are about 1 kilometer wide. So that's really cool to see these pits can be so large. But I'm going to show you a bigger one in a second. This one's on the order, it's even bigger. So down in this section, and here we have an example of that where it's uncovered, and so it's mostly exposed. We have Swiss cheese here forming right now, and this is a few meters thick of CO2 ice on top of what we believe is primarily water ice with some dust in it. And these polygonal terrain, so you can see a lot of polygons there. We believe this is because of thermal cycling that causes fractures in it. But what causes a sublimation pit is actually a sublayer of CO2 that we didn't detect until 2011. We used the Mars Reconnaissance Orbiter again, the shallow radar, of which I'm a team member and a co-investigator. SHARAD, you can't see the actual instrument, but you can see the dipole antenna that resides on the back. As it flies over Mars, we use it to send signals down to the surface and record the reflections that come back. It's just optics. It's the speed of light, using the same principles we have for other telescopes. But it reflects back, and we can use the reflections to learn about what's beneath the surface. So here's an example. You see the spiral troughs. They're exaggerated here just to highlight their detail. And beneath the surface, we have a lot of layers that are observed with the radar. And they can tell us great things about the climate history of Mars because we can see each layer and learn about the deposition or the accumulation of that time. So we can see how that changes through time. And this is an image of, again, from SHARAD, going from one end of the cap to the other. And this was really cool. We could see in the bottom of the section, the layers are very continuous, nearly horizontal. And when I say nearly horizontal, what I mean is that we have 2 kilometers of ice here, over 1,000 kilometers in this direction, so it's 100 times vertically exaggerated. So these are almost perfectly horizontal if you were to flatten it out. But near the top, we see some changes that indicate that there was a change in climate in the uppermost section. And so we can use SHARAD to understand what's going on beneath the sublimation pit. In 2011, I was part of a team that discovered what are thick CO2 deposits buried beneath all of this in the spiral troughs. And so here we have nearly 1 kilometer of CO2 ice that fills this basin. And then there's actually multiple reflections inside, what tells us that the CO2 formed or accumulated in different periods. And that means that we have a climate signal, a repeating cycle that we can see the CO2 deposition. And so what the sublimation pit is the CO2 that's been covered by water ice being exposed and subliming. We've been able to map out the extent of it, so that's what this black dashed line is. And we've been using SHARAD with a 3D processing to measure the thickness of it. And so up to the limit of MRO, which is almost 87.5 degrees, we have very fine resolution. We can see the thickness of it. Interior to that, we don't have any data, so we have to extrapolate. But we can see the thickness of this material, and it gets up to 1 kilometer right there. Here's a few more images from A to A prime here. We can go left to right. We can see the base of the CO2 and the top of it. And then from B to B prime, we can see it even better. And there's internal layering that tells us about this climate, where we have CO2, water ice, CO2, water ice, CO2, and then water ice, and then a very fine amount of CO2 on top. So we have this cyclical pattern that tells us about periodic atmospheric collapses, which is really exciting because we have periods where Mars, the atmosphere falls onto the South Pole, and then some of it gets trapped, and then a lot of it comes back, and it repeats. And so we can learn about the climate history going back, in this case, more than 500,000 years. I'd love to show this image. So this is the high-resolution stereocamera, HRIC again. The South Pole is approximately here. This is in middle of spring or early spring, where we have the CO2 seasonal cap on the surface, and it's interacting with the dust in the atmosphere and below. And so you can see what we call this kind of mocha color, where you have white ice and the dark dust interacting, causing this really beautiful image. There's also this crater here we call McMurdo Crater, and you can see lots of secondaries. But primarily, we see the spiral troughs in this region. And I'm zooming in again to give you finer detail. And here again, you can see some of the detail in the CO2 ice. Okay, if you zoom in, so in this region where we have the dark material on the surface, if you zoom in a lot more to use the thermal emission imaging system, or THEMIS, down to, we got 20 meter resolution with this instrument, we can see these really cool objects, or these surface features, that mimic the wind patterns. And so the winds are coming and they move around and they move like this. What happens is the wind is flowing over topography, and it's steered by topography. These are winds that are more dense than the atmosphere around them, and so they move quite a bit, basically downhill. And so that's why they steer like that. What we think they're caused by is explosions under the CO2 ice. So you have a frost that forms in the winter of a dusty CO2 ice. In the springtime, when it gets hit by sunlight, it turns translucent, so light will penetrate, and when it does, it warms the substrate. The substrate gets very warm, makes gas pockets, and then those gas pockets create enough pressure eventually that you can break through the CO2 ice, which is not a strong ice, and then it entrails dust with it and puts that on the surface in these spots. If the wind is blowing, then you get these elongated spots that are kind of V-shaped. Okay. There's other things we call spiders. I'll show you just in a second. This is an idea of what it looks like. This is a rendition. It's not an actual photograph of when you have CO2 ice in the ground, and you may have up to a meter of CO2 ice on the ground. And beneath that, you build up this gas pocket, and it bursts through, bringing dust with it. And if the wind is blowing, it'll move downstream. This is the South Pole, just off to the side. Here's some other images of that. If we zoom in more using high-rise, so THEMIS was 20 meters per pixel. Here we can get down to sub-meter per pixel. And you can see a lot of these fans that are kind of V-shaped. And so you can tell that the wind was coming from the top left and moving towards the bottom right. And here's again, we can see this. And so here we have mostly dark, smaller fans, but occasionally we have this lighter, wider fan. This might be due to some cleaning, where we strip away the dust afterward. I'm not exactly sure what causes this. We don't know for sure, and so we're investigating that. I want to mention that a colleague of mine has created a citizen science project mapping these fans. His name is Michael Aya, and he uses these fans and hundreds of volunteers to map the orientation to figure out which way the wind is blowing. With that, you can also get the wind speed, because you can model how high these jets should push into the atmosphere and how far that should travel downstream. And so we can use this to learn about wind speeds, mesoscale atmospheric circulations, and those things. So I mentioned spiders. A spider happens to be similar to the jets, although it's a repeating one in the same place every year. So you can see why they call it a spider. It looks like it has lots of legs. There's a dark material. These are the same jets and fans that come up. What we think is happening here is that you have the CO2 ice sitting on top of an existing hollow caused by previous years of bringing dust to the surface. And so this becomes a source for the next years to do that. And over time, you can build up these dendritic patterns where the gas flows through them until it finds a place where it erupts. And they get quite a lot of detail. Here's a bunch more spiders in a different region, still using high-rise. Some of them have fans and some don't. and we're still figuring out why that is. Here's an extremely complex one that we've tracked from year to year, and you can actually see how it changes by year. So looking at how complicated it is, early on it was just a few branches, and each branch then had branches, and then those branches had more branches. And so this is a quite complex spider, also known as an araniform. That's the technical definition. Araniform is just spider form. Okay, a grad student in Ireland is doing experiments to try to explain this, and she put in CO2 ice on top of sand and then cut a hole in it. Instead of fracturing it, she wanted to go ahead and speed up the experiment. And when she did, it did exactly what we'd expect, where it entrained the sand and then pushed it up. I don't have a video, but the sand would shoot many tens of centimeters into the air, and it would then fall down onto the sides. And so just a block of CO2 ice with a hole in it will create these features we call spiders. And so it was quite a well-designed experiment to show this effect. In my own lab, we're starting to make CO2 ice. This is a chamber that I've inherited and then upgraded quite a bit in order to make CO2 ice inside of it. Here we use liquid nitrogen to cool a plate. And that plate gets cold enough that the CO2 atmosphere inside the chamber freezes onto the surface and gives us the observations we're looking for. And so I'm going to show some images that are 1 second apart. And that's the important thing here to see. So I've got a camera inside the chamber. The camera is approximately here, looking down onto a plate. And so here we see the fractures. These fractures are caused by a thermal gradient. So as the ice starts to form, the bottom of it gets really cold. It's touching the plate with liquid nitrogen. But the top of it's closer to atmospheric temperature, close to what we feel right now, room temperature. And so it causes a thermal gradient that will create fractures. 1 second later, we see that the fractures have healed themselves in this region, but over here, they form new fractures. And 1 second later, we've gone back. So starting here, so in a matter of 2 seconds, we form these fractures. There's none here. These form and these heal, and then these form again and those heal. This is really impressive that CO2 can react so fast. It also explains how we can transfer from this dusty CO2 snow that forms a thick 1 meter or so deposit to translucent CO2. Because if it's fracturing or if it metamorphoses, which I think is what's happening for that thicker ice, it can recrystallize, in this case, within a second. Probably the thicker ice takes a little bit longer. But when it's hit by sunlight and gets that energy, it can recrystallize extremely quickly and then go to fully transparent. Okay, so I showed this image in the beginning. That's the North Pole. And you can see here, so this is back to Marcy. Marcy makes these great videos. We're going to track from middle of spring. So this LSB number is the date. LSB 0 is the first day of spring. LSB 90 is the last day of spring or the first day of summer. So we're smack dab in the middle. And I'm going to show you how the CO2 seasonal cap retreats back towards the pole. That's because the sun is coming up. You're also going to see some dust storms that blow out of this. So over time, you can see the CO2 is retreating. And then there's a few dust storms that'll pop out. These are the same ones I showed you earlier with the other cameras. Everything's frosted with CO2 ice, but it starts to defrost and expose the dunes. The dunes are extremely active in this period when it's extremely windy and there's no CO2 cover. And then by the late spring, LSB 90 is early summer, there's no more CO2 ice. We do have some dust in the atmosphere. And so this is just a really great way to watch this. I have a student working on this right now, and from year to year, he can see the same storms occur every time. And so that's a really interesting result. It means that Mars is very predictable, and we like that, because if we can make a prediction, write the paper, and prove it right, it makes us feel good. As you go into late summer, and then you get into fall, the CO2 starts to fall back on the surface again. And let's see if I wanted to show you. This is a really cool result that my student has come up with. So as we get towards this end of summer, we start to put CO2 on the surface again, and you can see in a matter of a couple days, we switch from where it's mostly white to you got mostly white and then there's some dark material here. This is the CO2 doing that really rapid transformation from really light to mostly transparent. And so this is a really cool property of CO2. And then there's, of course, more storms at that time of year. I mentioned spiral troughs. They have a wavelength of approximately 50 kilometers, although it ranges from 20 to 70 in some places. They're 400 to 1,000 meters deep. this is a really large feature. And there's a bunch of them. The longest one is 800 kilometers, but there are several that are many hundreds of kilometers. We can also see on the surface these wind streaks. Here's a few of them. There's some larger ones that do like this. Here's some more down here, and some more there. The wind streaks tell us the predominant wind direction throughout the year. And this is in the springtime when the CO2 cap is just retreating. We create these winds that are driven by density, and they're also reinforced by the thermal gradient. When you have a really cold temperature here and a warm temperature there, just like on the sea, you're going to have the air go up, it's going to circulate, and so you're going to have wind blowing from cold to hot. We're going to zoom in. So this is with an HRSC mosaic. We're going to zoom in using CTX onto a spiral trough. Here we can see layers exposed. We can also see some wind streaks, which is great. We're going to zoom in again. I should say it. This is layered terrain, and this is banded terrain. It looks a little different. It has to do with removing ice from here and then depositing it there. It doesn't look like ice because it has some impurities. Those impurities are dust. This is mostly pure ice, and this is up to a few % dust. The dust really changes the color of the ice. Okay, so here's another image from Themis. It's projected onto topography, so you can kind of get an idea that there's lots and lots of layers here that expose at these spiral troughs and at the margins where we have ice retreating. And each layer tells us about the deposition history and the climate at that time. And so we want to go sample these layers. We zoom in with high-rise. This is zoomed out for high-rise, but it's zoomed in from the other images. And we get some pretty fine detail. There's many thousands of layers. We zoom in again. We can see more detail. And we zoom in again. We see more detail. And so the layers aren't perfectly contiguous. They do have interruptions. And this tells us something about the composition of the ice. But as far as this is better than 1 meter resolution, at our finest resolution, we're still finding new layers. And so we suspect that there are layers that might be on the order of not necessarily seasons, but multi-annual timescales to see if we were able to go and look at it finally with a drill, for example. We expect to see that on the order of millimeters or centimeters. Okay. This is using Themis again. Here's a spiral trough. I've changed the coloration to show, because I want to highlight a feature that's going to change between this image and the next image. The wind is coming from the top, which is north, and south is down to the bottom left. These are taken, I think, 2 days apart. What you have here is the wind's blowing in, and at some point it causes this cloud to form. This is an elongated cloud that fills the bottom of the spiral trough. And the cloud here is optically thick, which tells us there's a lot of ice in there, enough to actually change the surface elevation by about 1 millimeter per year. So we've shown that these exposed layers are retreating by about 1 millimeter per year, and that down at the bottom where I showed that banded terrain, it's accumulating at about 1 millimeter per year. That's on average. Some places are faster, some are slower on the cap. This is another image of the cloud. It's actually got some great detail also from the wind streaks. These are vortices that are parallel to the flow. So north is up, the wind is flowing down into the trough, and at the bottom we have a cloud. The cloud is the same as this cloud. It's not the same photo, but it's the same principle what's happening here. And so we have the streaks moving in. At the bottom we have just a huge jump in thickness. It goes from about 100 meters thick here to 800 or so meters thick here. So a big change right at the bottom of the spiral trough. We're able to see with the radar, if we zoom in on the layers, I mentioned how we can see climate history, and there's a change in accumulation, a change in that migration of the troughs. And so the migration comes from eroding material here and putting it there. That's the millimeter per year. If you change from 0.5 millimeter to 1 millimeter, then you get a change in the slope or the trajectory of the spiral trough. And this is one of the troughs. This is another one. And we can see that in the stratigraphy. And we've been able to use that to show that about 370,000 years ago, Mars experienced a climate change from glacial to an intraglacial, where we are now. So we're in an intraglacial period on Mars. We published this in 2016. Okay, back to here. I'm going to show some detail in this section. These are dunes that are flowing over ice. And what we have is there's a lot of sand dunes there. The ice is on top of an old dune field that is solidified, but as the ice cap retreats a little bit, it exposes sand, and that sand can be removed from there, and then It can form dunes on top of the ice. So this is a really stunning image, again, by HiRISE. We zoom in more. This is an optical effect. It's not an optical effect. This is the actual color, right? So we have the dunes moving. There's some changes where you have this bright ice in between the dunes, and then other places where we have dust and rocks between the dunes. And so this is a transition from icy interdune to not icy interdune. And the dunes are all moving. So if we go back next year, they're going to look a little bit different. Here's some really cool dunes, also a high-rise image. This is what we call the fingering mode, where you have two predominant winds. One from, so if this is the dune we're following, one from this direction and one from this direction. They focus the sand to flow in one direction primarily over time. And you can see there's a lot of these localized Barkin dunes. What happens is when you don't have enough sand to form a full sand sheet, you end up with individual dunes marching over the surface. And the surface is not involved in the saltation that creates the dunes. Eventually, they get much more complicated when you have enough sand there so that they can connect. Here's some dunes that are covered by CO2 ice. I really like this image because it shows kind of the reddishness of Mars, the dark dunes, and also the ice gives you a little bit more reflection than you would normally get. They're all moving kind of towards the upper right. Here's another image of a similar location near the North Polar Cap. In this case, it looks like you might see trees, right? But they're not actually trees. If you remember from the south, when you build up enough CO2 ice, you can have eruptions. And it will entrain the stuff that's below and then deposit that on the surface. That's what you're seeing here. And so there's this dark dune material that was entrained when the gas pressure broke, and then it deposits it on top of the ice. And so you've got the pink ice, which is really not pink. It's got a lot of dust in it to give us this color. And the dark sand material is coming out on top. If we zoom in on this spot, you'll actually see in action one of these plumes that are caused by the eruption. So when the CO2 breaks, you train the gas. The gas entrains the sand and dust, and so you can actually see it as it's happening. And that's really cool. Here's some more where we have these things forming on the slip faces of the dunes when it's covered with CO2. So the CO2 acts as a geomorphic agent where it helps change the surface, primarily due to loading. When you put enough mass on it, the dune's going to slump a little bit, but also due to this gas pressure beneath. These are dunes, but they have these really cool streaks on them. So again, it's a high-rise image. We see on the backs of the dunes dust devil streaks, and on the front of the dunes, we see that, and we see these slope streaks. This puzzled us for a very long time. What would cause that? On Earth, we see gullies. Gullies are formed by water, but water doesn't exist when you have CO2 ice on the surface. It's minus 100 Celsius, minus 120 Celsius. It's not warm enough for liquid water, so what must be causing this? Scientists thought, well, maybe it's rocks. If you have a rock flowing down a hill, it can dig in and make these streaks, and that was a possibility. But then we remembered this is sand; there are no rocks there, and so this idea was thrown out pretty quickly. And then we started to see in more detail. There's CO2 ice at the bottom. That's not just a coincidence. That CO2 ice got there because it formed that trench while it was moving. Here it is again. Here's another one in the process of sliding down. This is done repeatedly, so it takes more than one CO2 block to do this. And actually, it's not just the CO2 pushing. There's another effect here. So here's a colleague of mine, Candy Hansen. She's on a dune. It doesn't look steep, but it's actually pretty steep. It's just the way the angle was taken. She has a block of CO2 ice. She lets it run downhill, and it forms a trench. It's not a deep trench, not in this case, but if you do it over and over and over, you're going to form a much deeper trench. What happens is, it's like playing air hockey. You have gas supporting this, and that's because the CO2 ice is supported by sublimation from below. It's traveling over the warmer dunes because they're black, and so they absorb more heat. It warms it from below, and then you get this effect where you're pushing gas away, and you kind of hover. As you push, though, you push away the sand. And so then you can create these streaks in that way. So that's how these things formed. That was really cool to figure out. That was only a few years ago that we really identified the process. So as I mentioned, on the back of the dunes, we see these streaks that are caused by dust devils. Dust devils are extremely prominent on Mars. There are some locations where we don't see them, but there's some places we see them multiple times an hour. Now, this is an example of one we caught from high-rise looking from above. Here's the cloud, so it's putting dust into the air. This is the shadow of it. And It doesn't look like it matches perfectly, but that's because the sun's coming from a low angle, and so most of the shadow you see is from the lower section, and there will be more shadow off to the right. And here we have, oops, is it going to do it? Oh, it's supposed to play. There it goes. We can actually see the dust devils move and form. So these are just in a few seconds. These photographs are taken seconds apart. We can see these things form. And with all the detail, we can imagine that you get a really complex crossing of these streaks. This is one, a place on Mars we found. Wait, that's a Jackson Pollock. But I put the joke in there because this is an actual image of Mars, and Jackson Pollock must have got his inspiration from Mars, because there's quite a lot of these streaks. One cool thing about them is that they can form in a single season, and in the next season we have a lot of sand, dust fall on them again. It covers them up entirely, and the next year they'll come back and do the same thing. So some last from year to year, but in some locations they don't last from year to year. Here's some cool ones. You get curlicues on top of dunes. Of course, near the dunes we have the most wind. We also have occasions for the dust devils to form. And as far as we know, they form exactly like they do in the American Southwest, where you have winds that are turning like this, and it just makes this little vortex of wind that entrains the dust as it flows over. Okay, so back to the dunes. This is cool. These are taken, I think, 1 year apart. We can actually see motion of ripples on the backs of dunes. The first time this was identified in 2012, which seems pretty recent, but it was this major breakthrough. We'd seen these dunes for decades. We knew there were dunes on Mars, but we couldn't see them moving. We took a really high-resolution camera and a lot of persistence and planning to be able to see these ripples change places. And so these can move on the order of meters per year. Here's another example. You can see the back of this dune is moving here, and the front of the dune is moving there also. And so 2006, 2008, 2011. So these are taken over several years. Each Mars year is approximately 2 Earth years, so 668 days is a full Martian year. And so we measure Martian seasons along that way. Here's another one where you see the ripples moving. We can see the front of the dune moving. It's pretty astounding. We can see this in so many places on the planet. Gale Crater is a good one. We also had the rover go in there. So here's Gale Crater, where we have these huge mounds. The rover is eventually going to drive up here. I think we're just now to this ridge, or we're somewhere near that. But in between, this was from the landing site, there are some dunes here, and the rover got a chance to go look at the dunes. This is the spacecraft. Okay, so from high rise, we were able to see this. It's very hard to tell, but this is the trace or the track that the rover followed. The rover is sitting here in this image between these two dunes. And I love this because as a geomorphologist, I really want to know what's happening there. And we learned that Mars has the same size ripples on the dunes as Earth does. These are a few centimeters in wavelength. It also has the large dunes that Earth does, which can be hundreds of meters in wavelength. But it has these weird ones that do not exist on Earth, and these are meter-sized ripples with the smaller ripples on their backs. This doesn't happen on Earth, and has to do with Mars' lower pressure. It's under 1% of Earth's pressure, and so the molecules travel in a different way that can cause the sand to saltate a little bit differently. And so it's a frictional drag that actually creates this type of ripple that does not exist on Earth. It's just really impressive. And every time we see something new on Mars, it's really it's astounding. These discoveries we have are great. So these are another view of the smaller ripples on the bigger ripples on the back of a dune. Here we have the rover wheel, and it drove over it. And is it going to play? Yeah, you can see the change. This is just one day. So the rover disturbed the sand, and it was windy enough that you can see all these ripples are moving and erasing the tracks. So if you're if you're Hansel and Gretel and you want to find your tracks, you better not drop this in sand right here, because you'll lose yourself. And this is the sand on Mars from the Curiosity rover. It's the same size sand we have on Earth, but if you remember from before, it's mostly dark sand. So the sand grains are olivine and pyroxene, rather than the quartz sands that we have on Earth, which are mostly clear or whitish color. These are going to be a lot darker. And there's other minerals mixed in, which make it this kind of reddish color. But the same size, mostly different mineral composition. We've got some great photographs of layering here, so we can look back at the depositional history of this crater and know that there were lakes there. That's what these are, lacustrine clay sediments. But I really wanted to show a little bit more ice, and I realized I have to wrap up. So these are craters that are forming today. We can see before and after photos and see that they expose ice. So Mars, we've seen, I think, about 800 new craters form on Mars. They're on the order of a meter or so. They're not really large. But when they do, if there's ice below, it'll expose that ice and leave ice on the surface, which is really cool to see if you like ice. Here's one. They followed up on it to watch. I don't know the exact time frame. I believe it was a little bit over a year, or maybe a Mars year, and we saw the crater form, and then over time the ice went away. And so it doesn't take long for the ice to sublime. Okay, that's it. Thank you very much for your attention. I really appreciate the opportunity to be here.
Thank you very much, Dr. Smith. Do we have any questions from the audience?
I was just curious, how long, so when you take a video or a picture of Mars, how long does it take to get back to Earth?
That has a lot to do with the sequencing of events. The spacecraft can take it and store it on board. Usually we do things in cycles of about 2 weeks. So for Mars Reconnaissance Orbiter, 2 weeks in advance, we say we'd like to make this observation. And then during the following, so that's 2 weeks early. And then during the 2-week period we're planning for, so almost a month later, the sequence happens and we acquire that observation. It stores on board until we have time to download it. You can't download always. Sometimes the spacecraft's behind Mars. Sometimes it's, right now we're at we're solar conjunction, I think, so we don't get much data. So it really depends on the data rates, and that has to do with where Mars is in its orbit and where Earth is in their orbit. When they're really close, you get high data rates. You can maybe get it back in a couple days. But sometimes it takes a couple weeks. But never more than a few weeks between when it's taken and downloaded.
Thank you for those truly jaw-dropping photographs. Absolutely outstanding. And based on the hostility of the Mars environment, I'm going to make sure that when I buy my condo there, I'm going to buy the top floor for sure.
Yeah.
But I wanted to know, other than hydrogen, carbon, and oxygen, although I know Themis and HiRISE aren't spectrographs per se, but indirectly, have you noticed any other minerals or discovered any other minerals on the surface of Mars?
So Mars is extremely rich with geologic material. We see clays, and clays probably formed in an aqueous environment, so there must have been standing water on the surface. And so we see phyllosilicates, aluminum and magnesium phyllosilicates. We see a lot of iron oxide, of course, from the rust, and the basalt, the black material that was volcanic material, we see a lot of that. The gases are primarily CO2. There's oxygen a little bit, nitrogen a little bit, and argon is actually a bigger component than you expect. So those are in the atmosphere. And of course, the atmosphere entrains a lot of dust, and that can go up and down depending on the season. But Mars is extremely diverse in its geology, just like Earth is. The one thing that Mars is really lacking from what Earth has is granite. And granite forms when you have subduction under a tectonic plate. It partially melts, and when that solidifies, that melt, it forms granite. And we found almost no granite on Mars. Another surprise is we have very little amounts of limestone or calcium carbonate. And that's because even though it has a carbonate or carbon dioxide atmosphere, it probably didn't have the right acidic conditions to form these limestone materials. And so Mars has almost the same thing as Earth in many cases, and then there are a few cases where it's quite a bit different.
Follow-up question on that. Here, follow-up question is, if we're looking at iron oxide, Fe3O2, or any of the ferrous fumates, have you considered the possibility of electromagnetic fields from Mars having an impact on the formation that you're showing us? Has that been taken into consideration? Is that even a possibility?
So I'm not sure that the Fe3O2 itself causes it, but there's pretty strong evidence that the dust devils are electrically charged. And so because you have a lot of things moving, a lot of friction, you can build up a charge on the dust, and then it gets entrained. And so there's many lightning strikes that happen during this. And if you were going to send a rover there, and we have, this will affect the operations of the rover. So it is electrically charged in that way.
Excuse me. Question from the chat room. When we actually go to Mars, will it be advantageous to place a base near the poles because of the dust storms?
So that's a really good question. I mentioned earlier how the poles were protected from the planet encircling dust event because the winds pushing off the poles were there. There are numerous reasons to go to the poles. One of them is because there's abundant water on the surface. Humans have to have water. We can use it to drink and shower, but we can also split it in hydrogen and oxygen and use that as rocket fuel to get home. Because of that, there are obvious advantages. There's also one, if you're standing at the North Pole and the sun never goes down, instead of having your solar panel flat, you can have your solar panels vertical, and you can get 24-hour sunlight. And so then you can use that to charge your drills, so you can run your drills, or you can convert the water and split it. And so there's a lot of advantages. However, there are some disadvantages too, and that's the winter. And the winters are very long, over 300 days. And so you wouldn't necessarily want to go there unless you could go for a short period when you can get all that energy and then move. So most often what we talk about is going to a place where we know the ice is close to the surface, not at the surface, but somewhere close to 30 to 40 degrees latitude in either hemisphere, but probably north, because the water ice is only a meter or so below the surface. If you can scrape off that material and you can get the ice, then you can get the high energy from the sun all year round, and you can also get the ice that you need. And so that's what we're looking at sending humans right now.
Question's almost related to that in the sense that I wondered, given your area of interest, what would be your dream mission, or what instrumentation would you like to see sent?
My favorites, if I may. I'm very much interested in the polar caps. This is going to take too long. Let's see. When I show you this image, it's because I really like this image. It shows you all these layers. If we knew what constituents were there, and we could go track it. So on Earth, we use radioisotope dating to measure the ages of layers in the ice caps, especially if there's volcanic activity. We can also measure individual layers to tell us about annual accumulation. So my dream mission would be to go here and sample all of these layers and tell you the exact climate history going back for millions of years. That's my dream mission for sure. There's a lot of things we have to do prior to that. So we have to know where the constituents are. We have to send a precursor mission that would go tell us what things are in the ice that we can even sample, because we want to tailor our instruments so that we can measure those specific radioisotopes. And also we need better observations from orbit, because a higher resolution radar will give us more detail, and we can choose our landing sites better that way too.
I notice that the geographical North Pole isn't at the center of the ice cap.
That's right. That's not easily explained. So the north is actually a little better than the south. So the geographic pole is about there. If you include this whole thing, it's roughly there. The south is actually quite a bit farther off. But there's a lot of local things. So this canyon didn't form in a single event. It happened when the ice cap was growing. Winds would funnel into this pre-existing location and just prevent ice from ever depositing there. We have reentrance where the winds are very active in this region, so they tend to erode right there. One thing to keep in mind is it may not look like it, but we also have, this ice is much thinner. So here we have 2 kilometers of ice. Here we only have a few hundred meters of ice. And so the climate is driven by a lot of things, including the tilt of the planet. And also, if you were able to look farther off to the side, there are volcanoes on this side where there are no volcanoes on this side. They set up circulations that drive the deposition, and so that'll change the symmetry of it. The South Pole is even more complicated because you have Hellas Basin on one side, and you have Argyre on another, and if you go 60 degrees away, there's nothing. So it sets up these currents that don't allow ice to form in one region, but do allow it to form in others.
Talking about on Mars, in terms of like activating, like working in this environment as a human, like you don't go to hurricanes. So
No, the strongest winds that we've measured are I think about 8 meters per second. And that doesn't sound like very much. But there are places we know that it's quite a bit higher. So on the slopes of the volcanoes, when the wind has a long time to go down, it's going to build up a lot of speed. It can reach, some people would say 40 meters per second, which is quite fast. You probably wouldn't put a human there, but if you've seen The Martian, you worry about winds knocking over your equipment and everything. Because of the reduced pressure, the strongest winds on Mars won't knock anything over. You couldn't fly a kite, even if it's 40 meters per second. It's just not enough pressure to do that. So the risk is really the dust that it brings with it, because the dust can be entrained and get in seals in your suit, get in your habitat, get in your lungs. That's the real hazardous environmental condition.
I guess back in the old prior to all this reconnaissance, it was thought that the ice layers were very thin. They went away and it was just rock underneath, I guess. And the impression that I had was that Mars had relatively little ice or even carbon dioxide, and it was a thin layer. But what you're saying is that there are like hundreds of meters or kilometers.
Yes. Yeah.
What would that mean that Mars has actually quite a bit of CO2 and water, and if it all melted, it would be...
That's a good question. From Earth, prior to observations in orbit, or even the first flybys with Mariner, we could see the seasonal cap come and go. So in the north, this will actually it'll go down to about 60 degrees. It would cover most of the image if we took it in very early spring. And so we knew that they had the seasonal effect, and it couldn't be that much. We knew they didn't have a lot of pressure. And so it couldn't be more than a meter or so thick. And that's the case. It just is about that. But in the case of the south, we couldn't really see the kilometers thick. We didn't have topography until the late 90s. And so we had to infer a lot of things based on what we saw. The south, because the water ice is not exposed, we thought we had this very limited CO2 cap with not much material there. In the north, I think we probably knew there was ice, but we had no idea to tell how thick it was. All told, the amount of ice on Mars, including north and south, and all the mid-latitude ice, which is buried, is about the same volume as Greenland. So there's actually quite a bit of ice on the planet, much more than we would have thought 40 years ago. For CO2, the current atmosphere is like 10 to the 26 kilograms in mass. The buried CO2 deposit I mentioned earlier, we found with the radar, has almost exactly the same mass. It's like 10% more mass than the current atmosphere. So we've heard sometimes Elon Musk will joke about nuking the south pole of Mars. He wants to do that to release that CO2 to double the atmospheric pressure. And if that would make it easier for humans, I think. So, yeah. Quite a bit more than we thought. There's another one. Right here.
Another question from the chat room is, where do you go? And follow up, do you like potatoes?
Great questions. I love that movie. The Martian is really entertaining. And except for the wind speeds knocking stuff over, it was actually quite accurate. I would love to go. It would have to be a quick round-trip mission. I would not go one way. I enjoy walking barefoot way too much. I enjoy eating cooked food rather than microwaved food. And so it would be a huge sacrifice to go for the exploration and to go see it. Yes, I love potatoes. And so, yeah, hopefully you wouldn't have to eat only them.
Your CO2 freezer machine looks super, super cool. But other than looking at the crystallization patterns that are coming and going, what else are you working on with that in your lab?
Thanks for asking. So I'm a new professor. I started at York University just over a year ago. And we're building this to eventually study all the types of ice in the solar system. But right now we're focused on CO2 because I have the most experience with CO2. Not just the fracturing, but we also want to study the reflectance properties in infrared and ultraviolet, because we can study them remotely on other planets using telescopes. And so I mentioned how the CO2 changes very rapidly on Mars. We can see it. We don't understand that. I'd love to understand that, and then I'd love to understand the reflectance properties. But eventually what I really want to do is grow nitrogen ice, because Pluto has nitrogen glaciers, and no one really understands them. And I'd love to grow nitrogen ice in there and see how it deforms and see what it does, because no one's even done any experiments like that. So,
What crazy temperature would that be?
that's a good question. So CO2 is 150 Kelvin approximately, so minus 125 C. To get to Pluto temperatures, you have to be about minus 200 or 210. So it's really cold. Yeah, you don't want to be in there.
Any other questions? All right, last one.
Hi. Do you, like, in your opinion, like, do you support the, like, Elon Musk's efforts to try to, like, colonize Mars?
Yeah, that's a good question. I get that kind of often. I support exploration of Mars, sending humans to Mars to learn about the science. He's motivated by putting humans on another planetary body. That personally doesn't motivate me. I'm just really curious about what's going on there. I want to understand the geology, the climate, the atmosphere, all the ice stuff. And so if we can send people there, the amount of work we could do would be so much greater in a smaller amount of time than the rovers. The Spirit and Opportunity were there for over a decade. A human could have done all that work in less than a week. And so we can learn so much. It won a marathon. It set a record on Mars Opportunity rover for going a marathon. A human can do that in a few hours. Not that we would and pick up rocks, but my point is that we could do so much more and learn so much more quickly. So I support that. If the humans are going for the scientific value, eventually something might threaten Earth from a meteor or something like that. I don't think that's likely in the near future. And so we do need to protect Mars. It has really interesting environments that once humans get there, we're going to damage them. So if we can observe them first with robots, so we protect them, once we fully understand it, then we can go and enjoy it without destroying it. So like a slower approach, and not just for sending people there.
Dr. Smith, on behalf of the Toronto Centre, thank you very much.
Thank you.
We'd like to present you with a little token of, now it's got some images, not quite as high resolution. And unfortunately, Mars is not part of the calendar this year, so you've got a few other things to look at now.
Thank you very much. Yeah, I really appreciate it.